Okay. Can you hear me, everyone?
Yes.
Okay, awesome. So let's get this started. Hello, everyone, and welcome to day 5 of the Climate Change AI Summer School. My name is Ruth, and I am an advisor for AI at the Fair Forward Artificial Intelligence for All initiative, funded by the German Agency for International Cooperation, or GIZ for short. I've had the pleasure to work with some of the folks from Climate Change AI, and this is, as a reminder, a global nonprofit that catalyzes work at the intersection of climate change and machine learning. I highly recommend checking out the material on the website and following them on socials. There's a Twitter link here, and to engage with them on the community platform. And if you would like, subscribe to the newsletter, which regularly shares updates and opportunities in the space. This year, I'm excited to be part of the summer school and introduce you to our housekeeping rules and our wonderful speakers of today, together with my colleague Aditya. Now, we welcome you to ask questions and actively participate. You can do that via the chat for general comments. Unfortunately, not all questions will be asked given the high number of participants. But if you have a burning question that you want to ask, make sure to use the Q&A feature. That way your question will be voted, and the more votes your question gets, the higher the chance it will be asked. You can also vote for other questions using the Q&A feature. So what's the schedule for today? We will have 2 lectures, one on AI for climate science, but by Jeggle, followed by a second one for another hour on AI for weather by Dr. Peetak Mitra. With that, let me introduce you to our first speaker for the upcoming session on AI for climate science by Jeggle. Kay has just finished his PhD at the Institute for Atmospheric and Climate Science at ETH Zurich in Switzerland, and his work focuses on using machine learning and satellite data to improve our understanding of cloud processes and their interactions with aerosols. Hi, the floor is yours. Enjoy the lecture.
Yes, thanks a lot for this nice introduction. I will quickly share my screen. Can someone just confirm that everyone can hear me?
Yes.
Okay, perfect. Perfect. So yeah, I will talk today a bit about AI for climate science. As Ruth already just said, I just finished my PhD at ETH Zurich, and I also am a core team at Climate Change AI for the last 3 years or so. And in general, my main focus is to use AI for the atmosphere, so especially clouds. To give you a bit of an idea what you will hopefully learn today and what you will know by the end of this lecture is to have an understanding of the key concepts of climate science, and then have a good idea how we can use AI for climate science on different use cases. Also, what are the key considerations and challenges of using AI for climate science, and where you can get started for your next project. So the focus of this lecture is really the breadth. We won't go into super much detail, but we'll cover a lot of different topics. And in the next lecture by Peetak, we go really into depth into one kind of application, which is AI for weather and climate models, which is currently big buzz. And yeah, this is how Peetak looks like, and you will find him later in the follow-up lecture. So please stay tuned for that. Before we start, I would like to get a sense of who you are. So if you could just take a minute to fill out the poll that the TA will start in a second, and just let me know where your background is. Okay, I'll just keep it on for a couple more seconds. Okay, I think we can close the poll and then also see the results. Okay, so we have quite a mixed crowd, both from climate science, 22% machine learning, 30%, 10% who work at the intersection. So I hope everyone can take something away today, and 40% from a different background. That's great. Yeah, I hope by the end of the lecture, everyone will know a bit more about the intersection of the two disciplines. So let's start in with a very basic intro to climate science. And I believe that you already heard a climate science lecture. So I hope it won't be too much new things and I will stay quite shallow here, but just that everyone is on the same page. So generally, if we talk about the climate system, we think about different components. And here you can see a simplified image of the different components that are the atmosphere, the hydrosphere, so all the water, the cryosphere, the ice, and the land surface. This is from the IPCC report. And in climate science, really try to understand all the different components, how they interact with each other on different scales, and how also currently, given the current situation, also how climate will change with the future. So here you see like many different interaction between the components, which makes it a very complex and difficult system to model and to understand. What we are interested in is also the Earth's energy budget. So we have energy in the form of shortwave radiation coming from the sun that's coming to us, to the Earth. And some of this is reflected by the clouds, some of it is reflected by surface albedo, and some is absorbed and then also re-emitted again as thermal radiation. And in a kind of pre-anthropogenic state, we usually are in balance with what is coming in and what is coming out. But now, due to the Anthropocene, we have an imbalance mainly caused by greenhouse gases. And kind of understanding all these radiative processes is also one thing that climate scientists, or especially atmospheric physicists, are studying very intensively at this moment. I already triggered a little bit, of course, when studying climate science. Nowadays, the main motivation for many studies is to understand climate change better. So here you can see kind of the projected mean temperature curves for different socioeconomic scenarios. So depending how we as a society decide to go forward, but we see that there is for sure a warming coming. We already are over 1 degree actually of observed warming. And as I said, mostly this is due to the effective radiative forcing of greenhouse gases. And here you can see the radiative forcing of different components. So you can see that carbon dioxide has a very big effective radiative forcing. So this is basically warming the atmosphere and the Earth. And we can see that the uncertainty bar is quite low. So here we are really certain or quite certain about the effect. It's only after digit numbers that we might not know yet. On the other hand, we have also aerosols that are emitted by combustion processes, etc. And they have actually offset quite a bit of the greenhouse gas forcing. So actually, if we wouldn't have emitted many aerosols, the Earth would have warmed even more. And that as we are cleaning up our industries, this effect will reduce and lead to even more warming. But here the uncertainty is really large. We can see for the aerosol cloud interaction and also the aerosol radiation. It's a bit less the uncertainty. So, and to also reduce these uncertainties, this is one big challenge in climate science and in general also forecasting weather and climate on all the different time and spatial scales. I can really recommend you all, if you haven't done so already, from the pre-reading material to read the executive summary of the IPCC AR6 report, which will give you a very good understanding of the causes for climate change and also the outlooks. Here I'm only showing the mean temperature because it's an easy number to digest, but actually extreme events, precipitation, everything is going to increase. This we are certain of. There's still some open questions. So the core things we have understood but in climate science in general, we are also interested kind of like in the regional dependencies, etc. Okay, so this is a very quick and fast primer in climate science. And I really recommend, as I said, to look at the IPCC report. It's a great reference. If someone wants to argue with you in a pub, you can refer back to the IPCC report. There you will find the answers. So now we are going back to, we're going to AI for climate science. And it's a really rapidly evolving field. This figure from a study from 2021 kind of shows the percentage of papers published in a certain domain, for example, earth science, which climate science is part of, contains keywords like machine learning or AI. And in 2020, it was like 5% of all published papers in that field. And we can really see this exponential growth. And if you would look to 2024, it would just continue with thousands of papers coming out every year. So it's really a field that is coming into a maturing phase, I would say. Or not really maturing, but it's just picking up a lot of speed, and you can see a lot of things going on. So it's really great to have you all here today. Okay, so why should we use, or why could it be a good idea to use AI for climate science? And here I would like to, for you to think a bit about yourself, like why would it make sense to use AI for climate science? And I would ask you to write just short answers into the chat. And we do this, I would say, for the next 2 minutes or so. Yeah, I see many answers. It's hard to keep up, but I think just to summarize a bit, I think there's a lot about better predictions, forecasting, as you save the planet, large data sets, speed and scale, reduce the cost of forecasting. Yes, very good. Okay. Yeah, I see that you already thought about the topic quite a bit. And really, thanks to everyone for your answers. It's great to see the different angles also of your ideas. And I'm not claiming here to be complete or to know everything. So just from my perspective, I think the main reasons why we use AI for climate science, or why it's a good idea, on the one hand, it's data. So we have, on the other hand, it's cost savings. Then we have research questions and urgency and impact. And I will go into all of these in more detail now. So first, we have a lot of data. If you think about big data, really climate data is where you can find it. So we have petabytes of data coming in from remote sensing, from satellites, from climate model outputs, with the models getting higher and higher resolution. The data sets, the model outputs get larger and larger. And also we have in situ observations, which of course are a lot smaller, but here we have really just a humongous amount of data coming in every day, and to kind of wrangle this data and to make sense of it, really AI can be a big help. Here you can see some images of a satellite, or ERA5, which is a reanalysis product, which combines model output with observations. Then also we have a lot of non-linear dependencies, and on many different spatial and temporal scales. And here for also machine learning has been proven to be good at modeling non-linear dependencies. Also, we have characteristics of the data. They have analogies with classical machine learning data. For example, we use like image-like data from satellites. We use time series data, for example, natural language processing. We use also time series data. So there is similarities that motivate using similar methods for this data. However, there are also key differences, which I will come to at a later point. Then the next, I would say, are the research questions. Like, what are the tasks actually that we're doing in climate science? And these also have analogies with classical machine learning tasks. we often want to predict something, we want to classify something, we want to detect an extreme event, for example, etc. So these are all terms that probably a machine learning engineer or knows by heart, and all these questions we also have to tackle in climate science. And there's this really cool paper by Reichstein et al. 2019 that kind of looks at classical ML tasks and translates them to the classical machine learning classical climate science tasks. And I will just give now 4 examples to give you a better idea of what that means. So in machine learning, a very common task that probably everyone who has worked with machine learning is the object classification, localization, typically done with natural images like cats and dogs, but also for autonomous driving, etc. And in earth science or climate science, we also have to do this, for example, in extreme events detection here in this dynamical system. Another common task is super resolution, where you want to go from a low res image to a high res image that looks realistic. And the same thing we do in climate science. We have, on the one hand, we have coarse scale climate models that are cheaper to run, but we have also high resolution climate models. And these then can be used for training the super resolution task. And in the end, we can just run the coarse scale model, use the downscaling, and get to a higher resolution. Another thing is video prediction, which is basically short-term forecasting that we can use for weather and climate model prediction. Peetak will go into much more depth later on. And then language translation is basically modeling a time series, which we often have to do also in climate science. And if we would bring this paper to 2024, there would probably autoregressive methods like we use now in all the large language models, which is basically also just predicting the next word. And we often want to predict the next state in climate science. So these methods, of course, can be applied or are heavily applied as well. Then a very big kind of motivation why to use AI for climate, and actually I read it also a lot in your comments, is cost savings. So numerical climate models, they are traditionally very expensive to run, and also other physics-based models used in climate science, and they are run on the most sophisticated high-performance computers in the world. And it's just very costly to run, to just simulate 1 year, for example. On the other hand, MN models, if they are having good skill, they can significantly reduce the cost, maybe just running on one machine or a few GPUs, and thus we reduce the cost and the time spent on the simulation, which then can lead to cheaper simulations that can enable faster projections and especially also larger ensembles. So you can do many ensembles, which can give you a better uncertainty quantification. Here in the image, you see, for example, the Pitt-Stein supercomputer that the universities in Switzerland use a lot for their climate modeling. And then lastly, also you wrote it in the chat, of course, the urgency and impact. I think it's also what draws many people to the field, which I think is really great development. I guess all of you are interested to contribute to tackling climate change. And we know, all of us probably know this graphic. It shows the deviation of the temperatures to the mean temperatures of the last 50 years. And we can just see that it's not looking good. And as I said earlier, we also want to look beyond just the temperature, but it's just a good indicator that makes pretty graph, but also all the other things like extreme events, droughts, precipitation, etc. They are already happening and impacting all of us. All right, so I hope I could give you a quick kind of understanding why it makes sense to use AI for climate. I'm not saying it's a silver bullet to solve all our problems, but it should be considered as a helpful tool for certain research questions. I'm now just giving a few examples that I selected. They're not trying to kind of cover the whole field, but just give you an idea what are a few different applications that we can use AI for climate science. And the first one that is probably the most obvious one and the one that has a lot of attention at the moment. I think, Ruth, would you like to ask a question?
Correct, if that's a good moment.
Yeah, sure.
Okay, so there's a question that came in from the chat.
Yeah.
About the energy use of AI models. It goes, do you have any idea about how energy intensive the use of AI in climate science compared to numerical climate models are?
Yeah. So this is a very good question that I don't have the numbers, but like from my intuition, we have to differentiate between two kind of stages. So the numerical model, it always needs the same amount of energy. For the AI-based model, it needs a lot of energy during training, but once it is trained, the inference is very cheap compared to a numerical model. And I don't know the exact numbers that kind of state-of-the-art AI models have used for the training, but from my intuition, if you look kind of at the balance sheet at the end, it's much less energy intensive as the high performance computing, just if you look at how much time it needs to spend on GPU cluster. And I can later find some references that have looked at this really quantitatively and share with you in the circle. Or the community platform. Yes. Okay, so let's continue with the examples. So AI for weather and climate models is really kind of like the first application that probably comes to mind when thinking about using AI. And here we differentiate between, I would say, two main branches. One is the fully AI-driven models. They're in the last 2 or 3 years, I think, or maybe 1 to 3 years, really there was like a revolution of performance. And I think a lot of climate scientists think about this differently now than a couple of years ago. But we really saw that different models were doing a really good job at doing, this is now short-term weather forecasting, I think up to 2 weeks. So you always have to remember also there are different scales between climate. We're really talking about long time scales and weather short time scales, and then there's sub-seasonal and seasonal time scales, etc. But for these short-term forecasts, these AI-driven models, they on some variables they outperform numerical weather prediction, and Peetak is really here the expert that will tell you more about it. It just would have felt wrong to not mention this at all. And we can have, yeah, as I said, much cheaper simulations. Here's just a visualization from the GraphCast paper, which is from DeepMind, which is one of the models that came out, I think, last year. On the other hand, we have AI as an emulator for subgrid processes. So here, it's really not about kind of replacing the whole model, but to replace some parameterizations. So we train a machine learning method to emulate a subgrid process from a high resolution model. And then we can, through this, increase the speed and also reduce uncertainties and error. And I think this is a really great visualization from a Christensen and Zanna paper from 2022, where you can see that in a climate model, like if you're talking about large scale climate model, usually the temporal scales, they are like 30 to 100 kilometers. But a lot of the processes, like cloud processes, etc., they happen on a much smaller scale. So what people do is they write parameterizations based on experimental data. So these are just like some equations that somehow represent some physical processes, but are actually not physically resolved in the model. And this emulator for subgrid processes can really improve these parameterizations and lead to better performances also for coarse scale models. Yes, I would take another question. Yeah.
Sure. I have 2 short questions that I think link very well to what you've shared.
Yeah.
One, you can choose which one you want to answer and if there's time, but one is about the open source aspect of these models. So the question came through the chat, are these models open source? That I believe came after the GraphCast model you mentioned.
Yeah.
But maybe you could speak in general about how many of these models are open source. And then the other question would be, can AI help predict turbulence for the aviation industry?
Sure. So I think the open source question, to my knowledge, most of these models are open source, but I think I would defer this question to Peetak later, because he really is in the weeds in this topic. And the turbulence question, yeah, turbulence in general is a difficult process to model. And I think it might, I'm sure there are working on this, because aviation industry, there's a lot of money, and where there's money, there's also research. So I'd be surprised if there isn't any research. But in general, I think the question is more, can we predict turbulence well? And then kind of the downstream task would be, can we use it for the aviation industry? But yeah, it's not my kind of core expertise, but I'm sure there is some things going on. But yeah, I think turbulence in general is a small scale phenomena. So if you model it, I think you always have two options. Like you can model it, or in retrospect, you can also look at satellite data that has a high resolution. But yeah, for modeling, you would need, I think, a very high resolution model, maybe like a regional climate model with a very high kilometer scale or less resolution. Okay, but yeah, again, here I'm not an expert on that topic. Okay, let's continue with the next example. And yeah, as I said, Peetak is going to do really a deep dive into this topic. So you can ask all your questions to Peetak, and he can call me out if I said any nonsense. Then the next application I want to showcase is AI for ice sheet prediction at the poles. And here there's a model called IceNet by Anderson et al. From 2021, where they want to predict the sea ice probability from different climate variables with an ensemble of UNet. So UNet is like a fairly standard machine learning method that has like an encoding arm and a decoding arm, and it has been proven to be quite good for like image segmentation, classification, etc. It comes originally from the medical field. And they basically use this fairly standard UNet architecture. They put in maps of climate variables and kind of previous states of the ice sheet to predict future ice sheet coverage. And it turns out it works really well. And here we can see kind of the forecast for 3 months, and kind of the red area is kind of where the model got it wrong. But it looks like they're doing a really good job. And I think this is really a good example, because they also operate, they use it in practice. It's a project by the British Antarctic Survey. And this is, I think, a really cool use case where AI made a difference. And now the last example that I want to show is some of my own work. It's called Ice CloudNet. So you can see some similarities here in the name, but here it's about clouds, and we use AI for sensor fusion. So we've used different satellites to do a 3D reconstruction of clouds. To better give you an idea what the problem is that we have on the one hand side, we have geostationary passive satellite, for example, Meteosat Severi, that gives you these really nice images of the Earth on a high temporal resolution. So every 15 minutes you get this image. The downside is that you only get the top view, so you don't really have any vertical information. On the other hand, you have polar orbiting satellites with active instruments like Calypso. They shoot down a LiDAR or radar, and based on the reflectivity, you can make some assumptions about the cloud properties really in the vertical space, and you get these nice profiles here that you can see in the image. The big downside is that it's very sparsely available. You have like the observation at the same location only every 16 days. So it's really not possible to do any studies about the evolution and formation of clouds, which is really important to reduce uncertainties in climate modeling. And the objective now is to fuse the strengths of these sensors using AI to give you a better understanding what the data looks like is that every 15 minutes we get an image like this. This is just like a small part of our domain. And we get 96 of these images every day. So every 15 minutes one. But for one day, we only have like one overpass of the Calypso satellite. So very sparse. And the vertical profile, though, it looks really nice. We can make some assumptions about the cloud height. What is we see some convective cell, we see a anvil cloud, etc. So it really helps us to better understand the physical processes. And now in this work, we used also UNet with a patch GAN, so like a GAN-like architecture to really recreate the whole vertical structure for a given image. And I stop talking now and let the images speak. So on the left-hand side, we see like the Siberi input, and on the right-hand side, you see the vertical reconstruction that our model is able to create. And this is now in contrast to only this one small swath that we had for a single time step. And here really the AI or machine learning really helped us to increase the availability of vertical cloud formation by a factor of over 1 million. And now other scientists can use this data to study cloud formation, etc. All right. So these were just some sample use cases for you to get an idea how broad the field is. And it's much, much broader than that. I just wanted to highlight that it's not only climate modeling, fully AI climate models. There's also a lot of other things going on in the space. And I hope I could give you a little glimpse on that. Now, I think this is really important to talk about considerations and challenges. And here I would like to ask you again, can you think of any key challenges and considerations that we have to think about when using AI for climate science? And we do the same drill again. Just write your answers in the chat, and we'll give this another minute or so. Please do hailstorms and AI and climate change. Yeah. AI can be biased, data, compute, data availability, causal effects can be different. Out of sample prediction, I saw somewhere. Yes, I think, again, really, really great to see all the answers coming in super fast. It's really hard to keep track. All right, I would say we continue. Maybe if you have time afterwards, we can all read through all the messages, but it's really great to see that it also aligns mostly with what how I think about it. So here again, I'm not claiming completeness, and I just spotted actually 2 or 3 things that I didn't include. But how I think about it, it's like an interplay of different things. Here again, I have 4 kind of main themes that I will go into detail more. So we have, on the one hand side, we have domain knowledge, we have data. I think the first thing that you wrote as well, we have the model architecture and trustworthiness. What I didn't include here, but I want to highlight it, is I think it also came up now a couple of times, is kind of the energy consumption of the models. I think we have also a dedicated session to this in the summer school, if I am not wrong. For sure, this is a very important topic. I wanted to highlight here more like from like a technical perspective, but for sure, I think best practice is always to report also the energy consumption and to think about if using a 50 million parameter model is necessary for a small linear dependency modeling. Yeah. Okay, so let's jump into different sections. First is domain knowledge. And what I mean by domain knowledge here is really like in climate science, you have the different disciplines like atmospheric scientists, hydrologists, and so on. So you have a lot of expertise kind of in the different domains that are really necessary to use. Some of you are domain scientists, then this is kind of not really so important for you. But if you come from a machine learning side and you think, okay, there's an open data set, I have the newest machine learning methods, I will solve the problem easy, I will guarantee you that after a few days, you will notice that you don't know a lot of things and that it's really important to collaborate with domain scientists. And in my perspective, the domain knowledge is really key to firstly define the scope of a project, like what are actually the problems that a certain domain struggles with, what are the key research questions that are important and will have an impact if they are solved. Then really important, what are the data sets that that are useful in that domain, and what are the features that are important. So oftentimes what I see is machine learning people, they just use all the features that they have, and maybe they do some data-driven feature selection, but not really think about it kind of a priori, which are the features that actually physically are important. And I think this really can make a difference if you take some time in the beginning to think about the data sets and the features. And then, of course, you can do some feature selection data-driven. But I think first, making up your mind what actually matters for like a certain predictive variable is a good idea. And then kind of what I referred to earlier is like the choice of model architecture. Like sometimes it's not important to have the best predictive skill, but maybe it's more important to have an interpretable model. So maybe it's easiest to just start with a simple linear regression, and you can interpret your regression coefficients and they have some meaning. And then you can kind of increase the complexity, but oftentimes it's not necessary to have the most complex transformer model, but a simpler model that with increased interpretability is more important for the task at hand. And lastly, I think to interpret the results, it's also really important to consult domain scientists. Maybe there's some process that you don't know of, etc. So what I really recommend, and it's also a bit biased from my own experience, is that really kind of like a constant exchange between domain scientists and ML scientists is really crucial. And I think now there is like a new breed of scientists that are really in the intersection and have knowledge in both domains. But still, I think this close interaction is what we need, and maybe even need more. And I think occasions like today are really great for that exchange between the different disciplines. Okay, now we come to the data. This I read also a lot in the chat. So typically, if we talk classical machine learning research, it's often about natural images like ImageNet, etc., or we have language. I think these are the two main kind of modalities. Of course, you have video and audio, but it all goes a bit in the same direction. And yeah, as I said earlier, there are analogies between natural images and climate data, but they are for sure not the same. So here you can just see like a satellite image from NASA, or some like the Earth system data cubed by ESA, just different variables in a three-dimensional space. And I think just by looking at this, we can spot some differences. And in climate science, we often use geospatial data. So if you look at my background, you can see also the Earth. So this is what we call geospatial data. So just like observations of the Earth, I would say, simplified. Often we have more channels than in RGB channels. So in satellite data, we have often multi or even hyperspectral data. So we can think about, is there value in the different channels than just plugging in the channels as like one dimension or input. Then we also have interdependencies on really many spatial temporal scales. And I think every scientist in like climate science, etc., they can agree with me that really the scales, this is where the devil sits, because often you have to go from, for example, in my domain for clouds, you go for micrometer scales to like thousands of kilometers. And of course, in this image, you cannot see micrometer scales, but often you have many scales in your data, And you also have dependencies, for example, teleconnections from ENSO that go like from one part of the Earth to another. So you have to really think about how to use that data and not just plug it into a standard machine learning model. And also just as a small point, the size of the images, for example, from the satellites, they are much, much larger than natural images. Also, we often have to use unlabeled data. So we just get this petabytes of data or terabytes of data, but we don't know really what is inside because it's not labeled. And they're really, I think there's an analogy like to kind of the large language models where also really self-supervised learning was kind of a key to kind of the current breakthrough that we are seeing. And also now kind of foundation models in earth science and climate science are picking up. And I think a big part of this is due to self-supervised learning. One thing that we have to consider as well, that data is often regionally skewed to Europe and North America, because this is where the most research institutes sit. And even though we talk about satellite data, it's global, the observations are more sparse in the global south, let's say, for different data sets or for climate model output that maybe they regionally model mostly Europe or North America. So this is also something to consider and also to actively change, I guess, in your daily work. If you're working with these models, then saying, okay, let's not just model Germany and Switzerland, let's go to the global south, because this is also where the bigger challenges and uncertainties are located. And this is not really consideration, but I think a good trend that slowly benchmark data sets are emerging. We notice from classical machine learning that you have ImageNet and all the other benchmark data sets. And in AI for climate science is now slowly emerging. For example, one famous one is WeatherBench, or now WeatherBench 2, where you have really standardized metrics and data sets for evaluating these weather and climate models. Mostly weather models here, but maybe Peetak will talk about it more later. And this is something that we need for more domains, not just kind of weather prediction. But I see it more like as the field emerges or matures, more of these data sets will emerge. Then model architecture. I think really important is, I think I touched on this multiple times, is the data characteristics in a research question should inform the model architecture. So for example, if I have tabular in situ data, or if I have spatial temporal climate model data, really is a different topic. So maybe on the one hand side, I want to use a model like a regression, logistic regression, or tree method, etc. And on the other, I really need the power of deep learning. So I think this is always the first question to ask. And then I think always, I think this doesn't only apply to our field here, but simple is better than complex. If your simple model can achieve something, don't go overboard. And also simple models are usually easier to interpret. I think I would take one question. Do you want to go ahead?
I'm happy to ask a question, Kai, and a kind reminder that there's 5 minutes left. So whatever you prefer. Would you like to wrap it up before we go into the questions?
Let's maybe do it like this. Maybe I will do 2 minutes more than 5 minutes. Let's see. Okay, then let's wrap it up first. So let's go to the second part of the model architecture. This again is more a trend that I currently see. So if you go like back maybe 5 years or a bit more, I think in our field, most people use purely applying ML methods that they see at the Europe's conference, proceedings, etc. For their tasks. So they just go like to the zoo of models, like a UNet, a vision transformer, XGBoost, etc., and throw the data at it. And I think there's now a change to really developing application data-specific architectures. And this is also where a lot of potential is for the future, if you're interested to get into the field. And just one example here is by Clemmer et al., also a CCAI core team member that developed this like positional encoder graph neural network to better represent geographic data. And this is just like one small example. to showcase that we're really going to like application and data specific model architectures. I think it's a bit similar to like the medical field. They also develop their own models, and even their models coming back to the machine learning community. So we might see a similar thing unfolding in our field as well. And yeah, big topic, actually probably the most important one, is trustworthiness. And by this, I mean that climate scientists, they are skeptical of the use of machine learning, I think for very good reason they are. First, machine learning is usually an interpolation machine. We are living now in a world of extrapolation with climate change. So it's important that we show why our models doing what they are doing, if they are robust, uncertainty quantification, etc. First, I want to talk about that machine learning is often black boxes, especially deep learning models. And one thing to alleviate this is explainable AI. This is also a field that it's, I would say, in its infancy, maybe not infancy, but certainly not matured yet. And here's just one example from a paper that is predicting land surface temperature anomalies, and then using XAI method, I think it's layer relevance propagation in this case, to kind of detect where are the sources for predictability for a certain output. And yeah, this is a big field. I'm only very scratching at the surface here. There are many, many different XAI methods that are also constantly coming up. So this is a big topic by itself, but one to look into if you want to make your model a bit more interpretable or explainable. Then another important point in our domains is that the ML models, they are not necessarily, or most often, they are not physically consistent. There's this discipline of physics-guided machine learning, so really blending the two fields. I'm just showing like this kind of rough overview schematic here, that we use kind of knowledge from physical systems and ingrain them in our machine learning models. So this can be, for example, by adding a term to the loss function, have some additional physical layers, etc., but trying to blend the two worlds together and make use of the physical knowledge that we have, because we already know a lot about physics, and we should use it. And the last point is uncertainty quantification. Just showcasing here this projection from the IPCC report again, and you can see in the shaded areas, this is the uncertainty bars. And this is what we should do as well. It's really a necessity in climate science. And in ML, just a few samples, not the solution to all this, but there's Bayesian methods. They're often used, for example, Gaussian processes. There's in general the big field of probabilistic deep learning with different approaches, and also ensemble methods where you just do a lot of ensemble members like they do in climate modeling, and then you kind of have like an uncertainty with the spread of the outputs. And then it's also important to think about epistemic uncertainty, which comes like from the model, which you can reduce by having a better model, so to say, an aleatoric uncertainty that stems from the data that is, for example, through observation errors, etc., or randomness in the data that you actually cannot reduce with a better model. I want to say that all these challenges, they're really intertwined, and they're all not solved yet. So I gave some example always, but there's a lot of potential for future research. So if you're interested to get into the field, there by no means these problems are solved, and there is a lot going on these days. I think I might skip this because you get the slides afterwards. And I just wanted to let you know, I put a slide together with some pointers. I believe you get the slide later. So if you want to look into a specific topic in more depth, you can have a look at these pointers that are, of course, a bit personally biased and are not a complete guide to the field. But with this, then I would like to end the lecture. If you want to contact me for questions or anything else, please feel free to reach out by email or LinkedIn. And yes, I would like to thank you for your attention. It was really great to also interact with you with the questions, and I would be now happy to take any further questions.
Thank you so much, Kai, for this very insightful lecture. I really enjoyed it myself. I hope everybody did. And we have a bunch of questions. So let me start with this one. It's a clarifying question.
Yes.
Is AI used to speed up the calculation for climate modeling based on physical models like WRF, so weather research and forecast model, or is it a purely statistical model compared to physical models like GraphCast?
Yeah, I think I tried to outline this a bit, that there is like the whole spectrum. So I think you have, on the one hand side, you have the purely fully AI-driven models, and they are also in some sense, they are trained on climate model output. So they're usually trained on ERA 5 data, which is like a climate model output as simulated with observations. And this is like the training data for these models. And so it tries to basically, or just learns by emulating this ERA 5 data. So I think this is like the one side of the spectrum. And then the other side, you have, like I said, these kind of climate models where you just have like a small, because climate models is not like one formula. It's like many components. You have the atmosphere, you have a cloud scheme, you have, if it's coupled, you have an ocean scheme, and you have ice phase, liquid phase. So it's many different things. And sometimes, or some works, for example, just to parameterize convection, because it's expensive to calculate within AI models. So I'm not sure if I answered the question now, but how I see it is there's the whole spectrum from like physical models that incorporate AI, fully AI models. And then, of course, there's also this physics-guided AI, which kind of also uses physics in the model, AI model itself.
Thanks a lot for this detailed answer. I'm sure we'll have also room on the community platform if you want to dive further into these.
Sure.
Let me ask another one. Speaking of emulating, AI as emulator for subgrid processes, would you give a real-world example application and a link, please, in case you haven't covered that?
Yeah, I think like what I just said, like convection, for example, or cloud microphysics are notoriously expensive for numerical models. So this is a real world example. I can link some papers later in the community platform. I think there's always like the difference between, okay, is it used in research versus is it used, I think, in operational climate models. So it's always also hard to say what is used already operationally, but for research, certainly this is convection and cloud microphysics are big topics.
Yeah, that makes sense. Thank you. Let me choose another one. Are ML models more, less, or as effective as numerical and physics-based models in adapting to constantly evolving climate, such as historical data becomes increasingly noisy and distant from current conditions/trends?
Yeah, it's a very difficult question. I would say if we would have a physical model that is perfectly representing the physical world, then of course the physical model would be better at that. But you have to know that the climate model is not completely physics-based. You have like the large-scale physics. It's physically resolved. But as I said, many processes, like for example, the formation of clouds, that is super important for the radiation. It's parameterized. So it's not physically resolved. I mean, now we're getting to higher and higher resolution. Now we're talking about 1 kilometer climate models, but this is super, super expensive. And I wouldn't now say one is better than the other, but of course with ML models, it's true that if we train on historical data and there's no climate change in the data, then we won't be able to predict the future so easily. But since we are also training it with, because climate change is not something in the future, it's happening now, right? So we have data of climate change. But of course, predicting into the future, you always have to think about, is this now actually, does it make sense? How can we, for example, there's one good paper that I also linked in the pointers that kind of transform the input variables, for example, relative humidity, to specific humidity, and this then won't change so much with the future because it's dependent on temperature. There's a paper called Climate Invariant Machine Learning. You cannot do this with every variable, but there's also put a lot of thoughts into how we can use machine learning in changing environments. But there's certainly a lot of work to be done.
Indeed, lots of future research and work to be done in the field.
Yeah, it is.
I think that comes out pretty clearly, right? But it's also exciting. You spoke a bit on accuracy and reliability during your presentation. We've got a question that asks, how do you evaluate the accuracy and reliability of the AI predictions in climate modeling and forecasting? Has AI in climate change achieved the reliability needed to take action in consideration of its results?
Okay, I'll try to entangle the question, but I guess with reliability, kind of like robustness is meant, I assume. So yeah, accuracy, it's one metric of many, and once you talk about like spatial data, then you're probably not so interested about like the accuracy of or like the regression skill of predicting a certain pixel, but you're more interested about like spatial patterns, etc. So you have to put a lot of thought into designing your evaluation criteria for your own projects. And the same is with robustness. Like you can, I mean, there are many methods how you can try how robust your model is. You can use some unrealistic input and see what is the output. You can kind of try to trim your distill kind of your machine learning model, etc. So I think the question was if the current models are robust enough to take action. I think we don't need machine learning models to take action. That's the simple answer to the question. I think to the main question is answered. We have to reduce the carbon emissions. But of course, if we talk about our climate models to predict extreme events, I think they are in the future a super useful tool because they're very fast to run. You can run them for many ensembles. So you kind of get a robustness in there as well. So if you run it for 100 times and the mean is kind of giving you a certain direction with a small standard deviation, it might be a good sign. But I also refer here again to Peetak, who is much more into climate modeling. I feel like this is currently the main topic in AI for climate science that most people are interested. And Peetak will tell you certainly more about. I just hope I highlighted also that there are a few other applications in the field.
Wonderful. Thank you. I guess there is a second question that links to this one and might make it a little bit more clear. I'd like to know if your models are factually better than climate models. Do you do hint casting, so backtesting as well?
Maybe we can take all the questions for like the climate model performance, etc., and keep them for Peetak later, because I think I'm not expert enough in that field. I'm an observer more in like the AI for climate modeling. So I think Peetak can be a better person to answer them later.
Thank you for that. We'll make sure to keep them for later. And then I'll close the session with one very nice last question. How do we convince domain scientists to work with us, ML scientists? I've been submitting proposals with no luck, so this goes into interdisciplinary collaboration.
Yeah. Okay. Yeah, I think at this point, you don't really have to convince anymore. I feel like 5 years ago, it was much more difficult. I think now every domain scientist, they have heard of machine learning and they have seen some cool output. I think they might be skeptical. It's not applicable for every use case. And I think it's good that they are skeptical because it's not solving all our problems. If we use it wisely, it can be a tool to advance science in different subdomains, let's say. But from my perspective, it's not the problem now to convince people. And secondly, I see a lot of funding call for proposals at the moment with AI for climate science, kind of as an umbrella term with many subdisciplines. So I think if you reach out to the right people and check out the right call for proposals, there's a lot out there. And there are a lot more people coming in. So I think the competition also becomes more, but I think there's no shortage of problems to be worked on.
That's fantastic to hear, I believe, and very encouraging in terms of collaborating across disciplines. So I think those are beautiful closing words. Thanks again, Kai, for this beautiful lecture. And thank you everyone for attending. And we'll be moving on to the next lecture in a second.
Thanks everyone, and enjoy the next lecture with Peetak.
Okay, Peetak, are you ready for the next session?
Yes, I'm ready. Can you hear me?
I can hear you, and I'd love to introduce you before.
Sure.
Thank you, everyone, for attending the second lecture of today on AI for Weather by Dr. Peetak Mitra. Before I introduce you as a speaker, let me remind you of the two ways of asking questions. That's either by using the chat for general comments or via the Q&A feature where your question can be upvoted. Now, let me introduce you to Dr. Peetak Mitra, who is a San Francisco-based technologist passionate about leveraging AI to combat climate change. He's also a founder of xCarter, a venture-backed startup that's building a breakthrough AI-powered weather intelligence platform for businesses. Exciting, and let's dive right in. Peetak, the floor is yours.
Thank you so much for the introduction. I'll start sharing my slides. Let me know if you can see them. Can you see the slides?
Yes.
Okay, perfect. Thank you so much, Ruth. Thank you, Climate Change AI, for having me here. And most importantly, thank you everybody in the audience for attending these sessions. Kai did a fantastic job introducing the amazing landscape of what is possible today with AI for climate, what are the challenges, and I'll dive deeper into the world of weather forecasting. And I'll talk about the differences between weather and climate forecasting. But again, because this is just a 1 hour lecture, it'll probably be at a very high level. Happy to talk more about these things offline or connect with the audience offline as well to answer any particular questions. Also, thanks to the members that took the poll yesterday. So that gives me a sense of like what the audience background is like. So without further ado, I'll dive in and I'll talk about what you will learn today, or what I hope you will learn today. So the first topic that I'll talk about is, the main differences, the main characteristics of short and medium term forecasts. So these are not climate forecasts. These are forecasts from up to the next few hours, to the next few days, to the next few weeks. And why these are important. I'll talk about these. I'll introduce that as well going ahead. As I said, I'll talk about the differences between weather and climate modeling, what makes this field of weather forecasting challenging, shortcomings of the current conventional approaches. By conventional, I mean first principles-based physics approaches that Kai also touched on a little bit, and then why and how AI is playing a bigger role. There's a lot of buzz about using AI for weather forecasting. You must have seen it around you. There are articles, there are efforts by big tech companies as well as small startups such as xCarter to use this tool, use AI as a tool to improve weather forecasting. So I'll talk about a brief overview of the revolution in the space, and then do my bit to demystify these AI models to kind of show that these AI models, while they are very powerful, while they are very useful, they are also pretty much very similar to what you actually see in the world of vision and NLP, just with a bit of twist that makes it suitable for it to use for weather and climate data. Again, I'll show some case studies of this being used in the short-term forecasting and how that is actually providing useful information than what was possible before. So those two cases would be extreme weather forecasting. We are all aware of extreme weather and how it's impacting our day-to-day lives. And also energy forecasting. As the world transitions towards more and more renewable, it is becoming that much more important to be able to forecast what the energy production is going to be like. And I'll talk about that in a bit more detail later on and how AI is being used there. And lastly, I'll talk about some open challenges, questions, and opportunities to help inspire some of you to keep exploring in the space, as well as share with you what I feel is are the amazing opportunities in this particular space. So Kai talked about it quite a bit, so I'll keep it brief. But we know that climate change is actually here. It's right here, and it's actually impacting all of us. And it's shifting the weather patterns everywhere. For example, if you look at the average temperature shift, even a mild shift from the normal, so to speak, would actually lead to a larger risk of extreme weather events. And this is something that we seeing growing wherever you are. If you're in South Asia, India has been experiencing a massive heat wave unseen that has been not seen in decades. Same with the US as well. Severe convective storms are ravaging through the Midwest. There's a heat dome in California for the next few days. There was a heat dome in the Northeast for the next last week or so. And there is as you must have noticed in the last couple of days, there is a Category 5 storm, the earliest ever recorded in the season that is hurtling towards the Caribbean islands. So that is like a proof point of like how the weather is shifting everywhere. And this is only the beginning. Even if emissions stop today, the weather will keep changing because of some of these changes are already baked in. And if you look at the US map of the 2023 $1 billion disasters that's put out by NOAA, you are seeing like an increasing number of these events from an average of 8 to 10 events that happened in the last decade. It has kind of risen up to about 25 to 30 events every, recently, and it's only going to go up from here. And this has real life implications. This has implications how this is actually raking up massive amount of damage, causing insurance to pull out from various different markets, causing real damages to lives and livelihood across the country in the US, but also around the world. You have very freak weather events like the Libya floods that happened last year, where a hurricane in the Mediterranean, went to Europe, came back, and had a massive damaging impact in Libya, caused a lot of damage to life and property. And it's only going to get worse as the world is warming more and more. We are at about over 1 degree Celsius warming, as Kai mentioned, but hurtling towards 1.5 and 2 degrees Celsius in the not too distant future. The frequency of these extreme weather events are only going to increase. We can see that anecdotally, but also this is what the research is telling us. So it's very important for us to be able to model weather or at least plan for what's to build climate resilience. So think of this talk as a where it fits into the entire Climate Change AI Summer School. It's about building climate resilience. As the climate is changing, there's not much we can do about it. So how do we become resilient as species and protect lives and livelihood? And how we can use AI to that effect. So before I dive into how AI is being used and why AI is useful, I'd like to introduce some key concepts for us to be on the same page about. So what are short and medium term weather forecasts? So basically a short and medium range weather forecast predicts the weather for a very, very immediate time frame. It could be from a few hours, like these are typically called nowcast models, or to a few days. A couple of days is up to is called short term, or up to 2 weeks in advance, which is called the medium term. So these are just terms to kind of like define the timescales of these forecasts. And then what do they do? The forecast actually gives you a detailed information of the weather patterns, the probability of high precipitation events, high wind events, changes in temperature, humidity, so on and so forth, heat index, and so on and so forth. So this is like, think of it as a forecast that will tell you what will happen in the next few hours to the next few days to help you prepare for what's coming your way. How does it look like? For example, this is an image from the NOAA SPC Storm Prediction Center talking about the hail, propensity of hail on April 26, 2024 in mainland US. And you can see like there's a higher likelihood of hail happening in some states in the Midwest. And it kind of like, it's a large swath of the region. And this helps folks, operational planners, to plan accordingly. Similarly, this is very recent from the forecast path of Hurricane Beryl, which is barreling towards Jamaica right now as a Category 5 storm. So this map is already outdated. This shows that it's a Category 4, but it's already a Category 5 as of this morning. So basically, just goes to show that how rapidly, the weather, rapid intensification of storms due to lack of shear and lack of all these other factors is causing these super humongous storms that come out of nowhere. And there are so many examples of that. Last year, Mexico had one very freakish storm that intensified over 12-hour period, which no model actually caught. And that led to a lot of damage. So, so this is what some extreme examples of like how AI weather forecasts or short-term and medium-range weather forecasts actually look like. And we are quite familiar with some of these things depending on where you are. So what are short and medium-term weather forecasts and how are they different from, say, longer-term weather forecasts? So basically, what the x-axis is the time scale of prediction. So you're looking at from minutes, from very, very recent forecasts to up to a few weeks in advance, few months, few years, more in the climate realm on the right side, more in the weather realm on the left side of the x-axis. And so if you could see this, that the more the weather space is within this is more of an initial value problem, which means that they are very much affected by the initial conditions. What is the current weather what is the weather at the current time determines what would be the weather in the next few days. And these are generally deterministic forecasts. I'll talk about that in a bit. And these are very much an initial value problem, whereas a climate forecast is generally a boundary condition problem, a boundary value problem. Basically, what it does is that it looks at it's not as sensitive to initial conditions. It's more sensitive to how the long-term radiation impacts are going to be, like what is the longer-term feedbacks between different aspects of the atmosphere, the oceans, and so on. That determines the longer-term forecast for climate. So they are although they use very similar equations, the equations are very similar, but they are treated differently. They behave differently just because they are looking at different timescales. And the key differences between them, and this is just very high level again, as I said, the weather and climate models are using the same set of primitive equations, at least for the large scale physics, but yet they really differ from each other from significant ways. If you look at weather models, they are very, very sensitive to data assimilation. So data assimilation is basically looking at the observations that you have from satellites, weather balloons, in situ radar observations, and so on, and using them to correct your forecast, correct within the assimilation window. And that is typically used as a starting point for weather forecast to make a prediction deterministically or probabilistically over the next next time period. And the resolution typically for weather forecasts is generally quite high. For example, NOAA's HER model, which is a convection allowing model, is about 3-kilometer resolution, 1 hour temporal resolution, which is much, much higher than what you see in climate models, because the goal of this model is to provide accurate information for a very short period. And then this also explicitly models the atmosphere, but represents the other aspects of the Earth subsystems as large parameterizations, because the impact of these subsystems are not that not that heavy on these on understanding the evolution of the atmosphere, so to speak, because you're looking at timescales that are much, much shorter. For example, just to give you a concrete example, so weather models inform when and where a storm front is located. For example, we are in the midst of a hurricane season or severe convective storm season, so it will kind of be useful to monitor weather models or use weather models to inform where these systems are evolving, how they're evolving, and when is the likelihood of an extreme event happening wherever you are. On the other hand, climate models, data assimilation also happens here, but also these happens at a much, much longer time scale. Lower resolution because these are expensive to run. You don't want to, you're running them for very long periods, so you don't want to use high resolution. As Kai mentioned, there is definitely a lot of amazing work that is being done in developing 1-kilometer climate models, but those again require massive resources, GPUs, and so on. That is currently still an active area of research. So in absence of that, most climate models are generally lower resolution, meaning there are larger number of parameterizations. So you solve the physics, for the big stuff, but then for the cloud physics, for the radiation physics, you actually use a lot of parameterizations, empirical parameterizations, which adds to a source of errors. And then you have these coupled models of subsystems, the atmosphere, hydrosphere, and all that. And that kind of is quite important and the central core of these feedback loops that climate models generally have. And then climate models, think of it, instead of informing when and where a storm would hit, or is evolving, it will inform how many hurricanes will happen in a given time period, or what is the average storm look like in a few years, depending on how the climate system is evolving, and so on. And they take into account things like the SSP scenarios, which are a measure of how much carbon we are putting out, CO2 we are putting out in the atmosphere. So those, so it's a bit more complicated. They serve different purposes, but they're equally important. But again, for the purposes of this talk, we will stick to weather models. So why are weather forecasts, how are they made and why are they challenging? So weather forecasts, again, are made by collecting data, so assimilation, and as well as forecast from NWPs. To estimate the current state of the atmosphere and understanding the physical laws that we know from first principles and parameterizations for subgrid scale phenomenon to predict how the atmosphere will evolve. What makes it challenging is the physics. The physics is chaotic. It's a nonlinear, for those who are aware, it's a nonlinear equation, PD, which makes it very sensitive to the initial conditions. And we do not understand fully all the atmospheric processes that actually makes forecasting quite challenging. We have an incomplete understanding, so to speak. We understand the large scale stuff. The small scale stuff is very highly parameterized, which is a leading source of errors for these forecasts. And then again, data collection, because these forecasts are dependent on data for simulation, there are major data gaps in the global south. Compared to the Western world, where historical investments have been made. Historical investments have been made in trying to understand and measure the weather in real time. So, for example, if you look at this plot by Noah Mattis, this shows on the top. This shows the black is basically areas where there is not a lot of data that's coming through, and this sparsely populated. Data points are regions where there is, large amount of data, so to speak, in the US and in Europe, where you see like the normal observations. There's like 80% of the sensors are actually providing data compared to the global south in India, Africa, and South America, where the data is actually very sparsely available. And again, parameterizations look like this, where our goal is to model the clouds very, very, accurately by capturing all the fine scale details, but the current resolution doesn't allow us to capture that. So it's very, the subgrid scale models are very parameterized, which is why you do not capture the effect correctly, and then which leads to accumulation of errors, which leads to forecast being wrong as you go forward in time. So what are the two main types of weather forecasts before we go deep again into how AI is revolutionizing this domain? So as I mentioned, you have the initial estimate of the weather from the observations from what you best know about the system at the current time. And from that, you can generate this thing called the analysis. Basically, you look at a forecast, you look at the current weather in a particular area, and then you correct it based on observations from these different sources, and you can create this thing called analysis, which is a best guesstimate or best estimate of the current weather state. There are two types of forecasts, which is deterministic, which actually predicts one trajectory based on the best estimate of the initial conditions. So this is shown in this figure by red, where given a particular start state, so to speak, given the particular initial condition, and again, these models are extremely sensitive to initial conditions, it predicts a certain outcome or certain trajectory at a particular time in the future. But that's not necessarily captures the uncertainty of the initial condition. And this uncertainty comes from the data itself that is collected by these sensors, but also, the data gaps, so to speak, because even if you have perfect sensors, you can't really have perfect measurements across the spatial topography and geography. So, and that's where it kind of leads to a forecast that is, while it's useful, it's generally sometimes way off from what is actually happening, doesn't give you the sense of the range of possible states of the atmosphere, and the uncertainties doesn't account the uncertainties that comes with the initial condition, because there's an initial condition problem. It is very sensitive to that. So this is where probabilistic models or ensemble models comes into play. For ensemble models, what you do is like you have all these initial conditions, and this is what is generally used in production in real life, is that you perturb this initial analysis with certain physics-based perturbations, and then you get some members. These are called some initial conditions in array of initial conditions. And what you do is that you take those initial conditions and create trajectory for each of them. And this is how the spaghetti lines look like. Gives you a massive, nice spread of the forecast uncertainty. And then you can capture the probability of a particular event happening. For example, a rain event, extreme rain event happening as 10%, or extreme heat wave happening at 25% in your particular area. And that's a lot more useful than having one deterministic forecast, because weather forecasts are, again, driven by physics that are nonlinear, very sensitive to initial conditions. So this is what generally is used in the industry. But for the sake of this talk, we'll stick to deterministic forecast because that's just a lot less complicated. And this, again, gives you a very useful estimate of the likelihood of the future weather state. And this is, again, the climatology, basically what has actually happened over the course of recorded history, to see like what would be the possible states that are possible within this particular realm, given the current state that you're experiencing right now. So now diving into the AFR weather forecasting world, I did see that some of you are coming from backgrounds that are not AI, do not use AI heavily. So I will just like spend a slide on talking about very high level what constitutes AI. So the goal is that in a classical programming method, so scientific computing, or basically using HPCs and physics-based models, you provide the rules. The rules are basically the equations. You provide the initial value, initial conditions, and so on, and you feed it into an engine. This engine is basically just like a numerical solver or something. It gives you some answers. Whereas in machine learning, what you do is that you take the answers itself, and these answers come from observations, years and years of observations. Kai talked about it. These AI weather forecast models typically use a real analysis product called ERA5 from UCMWF. So that's the best estimate of what the weather is or what the weather was at a particular time in the past. And you have the answers. You know what the weather was, and then you throw more data at it, like initial conditions and so on. And then let the machine learning algorithm, this engine, figure out what are the rules, basically. And these rules are nothing but decision boundaries. So basically, if enough data is shown to these models are pretty adept, especially the new ones like transformers and so on. They scale really well with data. They're pretty adept at understanding what impacts you can expect if you have a current initial condition that looks something like that has resembled historically. And this leads to the point of interpolation versus extrapolation, which I'll talk about in the second half of this talk. But that's an important consideration to ensure that models are just not able to just interpolate, but extrapolate to a weather or to a climate that is rapidly changing. So it's something that's very important to keep an eye out. But again, one thing that we need to remember: badly trained models are ubiquitous, and rigorously evaluating these model performances is very, very important. And I'll talk about that towards the end of my talk. So what makes atmospheric science the next frontier for AI? The field of atmospheric and weather sciences generates a lot of data, right? From sophisticated observation platforms that is becoming more and more available by private players like Tomorrow.io or SpaceX and others that are bringing into life these observation platforms to improve NWPs. So NWPs are numerical weather prediction, the conventional methods that are faster, better, more accurate, are running on GPUs. Even that gives you a larger ability to generate, high resolution NWP forecast. Leads to better reanalysis products such as ERA5, which is what is used to currently model these family of AI weather models. And just because this data set is like, the best estimate of what actually happened in the world in terms of weather at a past state. So it's really hard for NWPs to consume and assimilate all these new observations. Not so much for AI models. AI models are extremely good at taking multimodal data, taking data, scaling with data as well. Some of these models actually arguably do well or better with as you feed them more data. And this data is sequential in nature. So weather or climate as well, as a phenomenon is sequential, is a Markovian decision process. So the future state depends on the current state, and so on and so forth. And it looks very much like large language models. If you look at large language models, the entire goal at a high level is to predict the probability of the next word or the next sentence or the next sentiment. And it's basically very similar to what the weather and the climate data looks like, which is why some of these large language models like transformers, the T in ChatGPT, so to speak, is useful right off the bat for these AI forecasting tools for weather. And there's sufficient complexity, right? Like, for example, if you do not have complexity in the data for AI to learn, and if you throw an algorithm at it, it will really possibly not learn anything, probably overfit to the data, and that's not ideal. So basically, you need a couple of things, right? You need a good algorithm that has complexity for or ability to present complex data, but also data should have enough complexity in them for this algorithm to be fully leveraged. And again, NWP's large-scale governing equations are very poorly parameterized. Large-scale governing equations are known, but the small-scale physics are poorly parameterized. So AI models can actually help in recovering some of these local parameterizations. And there's some amazing work coming out of Google research. If you're interested, check out Neural GCM. That work talks about building climate models where the physics is still being solved by the partial differential equations, but the parameterizations are solved by AI, and has shown some stunning results for long-term climate projections. And again, NWPs are tuned into data-rich regions like the Western world, so to speak, which is why they are a lot more accurate in those parts of the world. Whereas for the rest of the world, it's generally is not able to pick up nuanced weather effects or impacts. And the biggest opportunity for using AI for weather is the inference. Inference is orders of magnitude cheaper than NWPs. By some estimates, it is about 10,000 to 40,000 times cheaper than running a single NWP simulation, which makes it that much more exciting, because you can then run a larger number of ensembles to predict to better estimate the probabilistic weather that's going to come your way. And I'll talk about that in a slide towards the end. Again, this leads to better estimation of forecast uncertainty. Okay, what is something? Okay, sorry. So before I dive deep into this, I'll talk about AI weather models. I just want to limit the scope of this particular topic. So again, weather models vary a lot in scope, vary a lot in abilities. There are global weather models like ECMWF's IFS, Integrated Forecast System, which has a lower resolution, about 25 to 31 kilometers, but again, a larger time step as well, but gives you a global forecast of weather. There are mesoscale models that, like WRF, that look at regional areas. There are convection allowing models as well, like HER, ICON D2 from Europe, that actually are very high resolution, but only looks at very small regions like continental US, and also looks at forecast and provides forecast at a smaller time step, but only up to 18 hours or 36 hours and so on. So beyond that, they are also they also operate at a very high time steps. So there's a wide variety of models. You can build models for anything. You can build emulators, AI emulators for any of these models. But for the current focus, we'll just limit ourselves to the AI weather emulators for global models. Basically, AI weather models that are trained on ERA5 data. And these will be all deterministic forecasts. You can easily convert them into probabilistic forecasts by running a larger number of ensembles by looking at perturbing the initial start states. And that's, I would be happy to direct you to some papers that do that and lead to some fantastic, interesting results in the space. So how does this typically work? So this is, again, deterministic AI weather models. The experimental design is that the model is trained to predict the next sequence of events. As I mentioned, weather is very much a Markovian decision process. So and these models are defined and designed as such. So it's a very initial value problem. And then it is oftentimes autoregressive. Autoregressive means that it produces the next state by itself and then uses that state to produce the next state for the next time. Or in case of nowcast, which is basically just like, predicting precipitation at a certain particular time range, it's just the next scene prediction. It does not do a rollout. So basically, it can do both. For data, they typically use reanalysis products such as ERA5 or observational data like satellites or MRMS, which is radar data for nowcast. Characteristics are basically they retain the core elements, which is data assimilation to initialize start states, but instead of predicting the entire weather state, for example, if you look at a physics-based model, it has data across hundreds of pressure levels. Pressure levels are basically the altitude. Think of it as the altitude in the atmosphere, to give you a sense of what is happening in the entire atmosphere. But for most AI weather models, they typically only do a subset of these key prognostic variables, which are important for the weather on the surface, because that's where most people live and that's where most industries operate. So basically, they only produce a subset of these key prognostic variables. And there are many amazing AI-based techniques that have been proposed: ForecastNet, GraphCast, MetNet, PanguWeather. We'll talk about a couple of those in the next few slides. And this is how the data assimilation looks like. For example, if you have a previous forecast from a particular model, which is shown in blue, and you have observation coming in from your satellites or radar or and in situ sensors, what you do is that you use those observations to correct your forecast and then produce within the assimilation window. And every forecast that you see from ECMWF or NOAA has different assimilation windows. So based on how long is your assimilation window, you take observations and corrective forecasts from there, and then produce a new corrected forecast, basically, that will be a lot more accurate, a lot more sensitive to the initial conditions of the weather state itself. And this helps. So this is quite important, and this is what is used as an initial start state for the AI weather models. AI weather models take this particular assimilated forecast as a starting point. You make the forecast for the next set of hours or days, whatever you are trying to forecast for. A schematic of a typical weather forecast looks like this, where as Kai mentioned, that instead of having a red, green, blue channel, you have channels of various different physical properties, like U10, V10 are velocities, U and V directional velocities at like 10 meters, T2M is the surface temperature, and so on and so forth. Total cloud water vapor, total column water vapor, and so on. And what you model it is as is a vision problem, but with a larger number of channels. Basically, this is like a video problem where you're trying to predict a next scene based on the current scene. But instead of just having red, green, blue, you have a lot more information in these particular channels, which makes this data very high dimensional, noisy, because not all inputs are going to be useful. And it makes it very hard for it to kind of, that's some of the challenges that comes into modeling these data sets. You also can look at satellite data and radar data, and there are works like MetNet that have done that. And then you use all of the data at time t equal to, at the current time t, throw in your AI model, which could be a mix of transformers, neural networks, autoencoders, CNNs, LSTMs, and so on, and produce a sequence of what would happen for each of these particular channels at the future time delta t. And this is typically how it kind of looks like for the schematic of AI weather forecasting. The models change, but the data generally looks very similar to this. The framework generally looks very similar to this. So this was introduced very briefly by Kai, but again, how good are these AI models? Before we talk about them in a bit more detail, how good are these? Is it worth even exploring? For example, this is a work done by Google AI called Weatherbench 2 that compares the ensemble mean forecast for physics-based models with ML-based models for a different lead time for different variables. And you can see that the ML-based models, the GraphCast model by Google, is actually really, really good for most of these variables compared to even physics-based models or even ensemble means, which is quite encouraging to see, like how AI-based models are able to learn the dynamics just by looking at the data. These are all purely data-driven models. They see data as input and output sequences and learn the dynamics themselves. There are obviously things happening at that core, which I'll talk about in the next 2-3 slides, but these models are extremely encouraging. These results are extremely encouraging to see that this is actually much, much better. And if a climatological data, if it's just a climatological performance, it actually shows it's much better than that, which is basically quite amazing to see as well. So these AI models show promise. The question is, how do they work? And let's try to demystify some of these models and learn some common modes of learning. So basically, most of these AI weather models, the revolution really started from the first paper that came out in the space called, or one of the earliest papers that came out in the space called ForecastNet by NVIDIA, by Peetak et al. That talks about how they were able to show for up to 2 days how transformer models were actually able to perform really comparatively to the physics-based models for for very many key prognostics. The question is, how does vision transformers really work? This is again from a blog, which is quite useful if you want to learn more about it. So basically, just similar to this, like an image where you take one channel. For example, if this is the U10 velocity, data for your particular grid, your 2D grid. What you do is like you break it down into different patches. You have them, you add positional encoding and so on. Basically, positional encoding gives you a sense of like how they are related to each other in these patches, because as an image, you can see how they're related, but when you pass them on as a sequence of just a small cutout data, you don't know how they are related to each other. So that gives you a sense of how these data sets are related. And then you have a transformer model at the core, which is actually one of the models that revolutionized the field of NLP and vision and so on. Uses this mechanism called self-attention, which compares all these particular tokens with each other, which is how some of these models are able to learn teleconnections, long-range interactions, as well as influence of these particular patches compared to each other. These models are basically using this very simple elements like convolutional operations and so on. And again, self-attention is the key element here, which is then, which has shown to perform really well for even modeling very complex tasks like weather as well. If you're interested, I would encourage you to look at this blog, but also read some of these papers that are, there's some amazing stuff out there about transformers right now. So this is exactly how the weather, at least ForecastNet did and other folks have done, is that to take data from for various different channels and split it into patches, pass it on with a position embedding, and then you model the resulting sequence with a transformer core. But the big problem with transformers is that the training cost increases quite heavily as you increase the image dimensions and as you increase the number of patches, which is one of the disadvantages. But again, it scales really well with data. So there was another innovation in this particular space. Again, this is all coming from computer science and folks that are necessarily not working in weather, but working in vision. This is called swim transformers. The swim transformers basically uses this thing called a shifted window, which is, so for example, you do the same thing. You have a patching that you do for your data, but then you move around this, you change the shape of the patching. Basically, you kind of create these small local windows to observe to look at your data and basically use that to compare different pixels with each other. For example, on this side, you are comparing this particular pixel with data within this particular bounding box, this local window. But again, this particular, when you shift the window in another layer, you're actually comparing it to other data points, other pixels, so to speak, other patches, which actually helps it to learn and make it a bit more robust. One of the key advantages is that this reduces the computational complexity to a linear instead of a quadratic that you see in terms of transformers. And again, instead of applying global self-attention with transform models too, it only applies attention to within this single window, so to speak. So it compares only the data that is within each patch, each window. And then, because of it, it can actually focus a lot more depending on how deep your swim transformer network is to be able to model these long-range interactions. But again, that long-range interaction should be within this should be contained within this particular window. So there's an empirical estimate of how big this window should be. But that's, these are some of the two models that are two frameworks model that are quite popular in this particular domain. Some examples of these models. On the left, you're looking at the forecasted model, which is doing the exact same thing, whereas you have the data as a 2D grid data for various different features, and then you add the patch and positional embedding, have some mixing done between your channels and your spatial mixing just to look at the interactions between various different features. They use some additional Fourier transforms to learn the data in the Fourier space, to learn the embeddings in the Fourier space, but Apart from that, it looks basically just like a transformer model. And then that produces the output at a particular time in the future. Whereas Spanky Weather, instead of doing, modeling the Earth as just a 2D grid, it looks at surface variables, which is as a 2D grid, but also the pressure level variables. Pressure levels are basically the atmospheric variables, and then does some encoding, and the reason the encoding is done is to reduce the noise in the data, to reduce the dimensionality of the data, because learning data as is at this high dimension is actually quite complicated. But then after the encoding is done, they generally only use a vision transformer model at the core, a swim transformer model in this particular case, to learn this efficiently, to learn the dynamics efficiently. So basically, if you see, even if you use a different model, even if you use a different way of feeding the data into the model, the core is basically the same. You use some embeddings, you use some position encoding, and so on. Use a bunch of AI models, basically like transformers, graph networks, and so on, and learn it and learn all these things in a reduced latent space. For example, just talking about the common modes of learning in these models. And this is again the GraphCast model, which is one of the better ones that are out there, which uses a graph model. Again, the approach is the same, where you use an input weather state, you encode it in a lower dimension space. You learn the dynamics there, and then you decode it back to the high dimensional space for showing the forecast again for doing the rollouts. Again, so key features of all of these models generally include embeddings, because they help in efficiently learning the near and far influences. And this is important because if you try to learn the entire world, so to speak, the weather of the world in one go, it's going to be very, very expensive. It's going to be challenging. And that's probably not important, because the weather at a particular region is generally not influenced by weather everywhere. So there's a sphere of influence depending on how far you are forecasting that you might just want to limit your interactions to, which is what swim transformers do or graph networks do. The encoder decoder block seems to be very common, and these are useful to efficiently learn dynamics. There is a ton of research out there that has shown that this data, which is very high dimensional data, if you encode it in a reduced space, it actually limits the noise. It helps remove the noise from the data, and helps limit the interaction, basically reducing the high dimensional data into a smaller latent space actually helps in a better learning for these dynamical models, so to speak. And these models are generally based on very similar layers, CNN layers, graph layers, or attention-based models. So it's nothing like out of the blue, nothing that you might not have seen if you are in the world of ML. So there's not much customization that is happening, except for how you feed the data and how you pre-process the data. There's also a lot of these models actually use this thing called recency bias, which is taking the weather from the most recent time steps, so maybe 2 time steps or 3 time steps, and then feeding it to the data, because again, the weather at a future step is very, very correlated to the weather at the current step. So some of these models actually use more of these current weather steps, so to speak, and use it to forecast the weather at a future time step. And then loss functions generally are between the L1 or the L2 norm losses for deterministic forecasts. And so basically, if you take a step back and look at it, this is nothing specific to weather here. There is these key dynamics, these key features that you can see across all the models. And if you are familiar with any of these models, even CNNs or graph nets, you can actually build your own AI weather models to, because the data exists, and the rest of the stuff is not that complicated, so to speak. So there's other alternatives where you can actually use weather embeddings. So weather embeddings, currently most AI weather models produce a bunch of prognostic variables. But sometimes what you need is a diagnostic variable. What I mean by that is sometimes you need weather-derived quantities. For example, if you have a precipitation depends on the weather state. So you don't really model precipitation as part of the core weather in AI weather models. Whereas it's to model this separately is quite expensive. And we wrote a paper about that, so you can go read it if you're interested. But then weather embeddings for the prognostic variables are quite useful, and using those, you can actually extend your own weather models to include forecasts or include projections of any particular variable, reduces the deployment and training time by quite a lot. And the challenges are that you can only limit your forecasting paradigm to diagnostic variables and not model prognostic variables. Some quick case studies. So case studies for AI weather is extreme weather. Again, as we know, there's a rising occurrences of long tail high impact weather events causing massive damage, and using just deterministic forecast might not be helpful. So we could potentially use these very fast learning AI models by slightly perturbing the initial conditions to get a better estimate of the probabilistic behavior, something AI is very, very good at. For example, this is a this was a GIF. Okay, so basically on the left-hand side, you're looking at a very, very rare storm that happened on the coast of California last year. Tropical storm Hillary, almost never happens. Once in 100-year storm, cyclone, hurricane in this part of the world. And then on the middle, you're looking at the GF as a physics-based forecast that issued about 6 days ago. What would be the trajectory of this particular storm? And you look and the actual storm trajectory is laid in the cyan color. And you see that the physics-based model is actually predicting the forecast, the storm to actually not even hit California, to go along the coast. Whereas an AI model forecast about 5 days ago was able to accurately nail the trajectory for what actually happened. So just to kind of reiterate the point that while AI models are good at interpolating, if you have, they are also very, very good at predicting rare events like this, because if you are modeling the entire subset of prognostics of the weather, they are able to find that relationship quite accurately compared to just using physics-based models. And then for short-term convective events like rain, precipitation, on the left-hand side, you're looking at radar data. In the middle, you're looking at the data from the data from a machine learning model called MetNet, and HLF is the actual physics-based model. And you're seeing like the physics-based model is not showing the extent of the forecast as much as the AI models are actually showing for extreme weather events like rainfall. And again, this is, if you look at the architecture of this model, they are only using conval STMs, convolutional models and LSTMs and so on. So this is nothing out of the extraordinary. This is basically just using the same core elements of ML. So anybody that's working in ML can actually read and understand these things very well. There's nothing weather specific in this particular case except for the data and the physics. Basically, the need to respect these physics. So there's other case studies for AI for energy forecasting. If you look at this particular plot figure, that's actually from Intel, which is showing the risk of grid failures in the major grids in the US. And if you look at the central part and most of these parts in yellow, these are at risk of shortfalls at peak conditions, just because of the higher demand on these grids because of data centers and stuff, but also extreme weather events. And for this, AI can play a very important role. For example, AI can use these ensemble techniques to predict what is the probability of high long tail events. But also, as the energy mix is shifting to low carbon, carbon-free types alternatives, it is very, very important that we are able to understand the weather and use that information, use that weather forecast to guide the grid operators as well as the producers to be able to make decisions better in terms of balancing the load and balancing the grid. This is a great paper that came out at NeurIPS last year, which is about forecasting day-ahead solar irradiance. If you look at the particular thing, they only use transformers, a lot of encoding and so on, positional encoding and so on. And this is really useful for day-ahead commitment for grid operation and operational purposes for solar farms. So this is like as the grid transitions, as we need the grid to transition to renewables, AI will continually play a major role in operating for operational planning as well as grid planning and so on. Again, this is a very cool GIF from Google that talks about how if you actually use just a few different members of Ensemble, you can get some predictions for what the future state of the weather would be. So basically, these are think of it as initial conditions of the weather, and these are like the projections of the forecast. This is a probability distribution of what is actually happening. Whereas if you actually use generative models or diffusion models, you can predict a much larger set of possible outcomes, likely outcomes, which helps you manage the risk that much better. I would encourage everybody to take a look at this particular paper, especially diffusion models. I think I'm running out of time, so I'll quickly talk about this particular slide. So, we talked about how AI weather models are so good and all that, but while they show great promise, they cannot fully replace NWPs because AI models actually depend on NWPs for the initial assimilations and for the initial start states. They provide novel information, but they are not at the point where one should consider replacing NWPs with AI models. The challenge with AI models is that AI models are being proposed every week. Every 2 weeks, every 3 weeks, there's a paper by some research group or some industry labs that talks about a new AI model beating the state of the art and all that. And it's much faster than conventional NWP development, which is developed by scientists, and it takes about a few months to a year. There's a lot more rigor there compared to AI WPs. So that's something that we need to keep in mind, that there's a lot of noise in the community that we need to sift through. The best AI weather prediction models is not obvious. Different models have different behavior, different strengths. So we need some standardization in this particular field, and then many ML techniques work out of the box. So you take a CNN model, you can model rain for the next few hours quite accurately with a very, very simple CNN model. Forget about transformers, which are a lot more powerful. What are the opportunities within AI weather models, right? So AI weather models provide a novel information, just not emulate NWPs. I need to give credit to my colleague Vivek here. So basically what this plot shows is on the x-axis is the lead time, so number of hours in the future. And this is the error for a particular variable called Z500. And as you see, the error grows for different trajectories here. For example, IFS is a physics-based model. IFS ensemble is the ensemble of the IFS model, which is the most accurate model out there. HealWet is our forecasting model, which is an AI-based data-driven model. So what happens is that if you actually take AI model and just add naively to the physics-based model, you have a much lower error than compared to any of these models by themselves, like IFS and HealWet. While HealWet is better than IFS for particular lead times, but if you just ensemble these two models itself, they are a much lower error than either of them on their own. Still, IFS ensembles beats them, and there are reasons for that. But the point is that this shows that AI models learn something valuable. They learn something orthogonal to the physics models. So it just not emulates the physics models. So this is something that we could potentially leverage to build more informed ensembles and so on. Some of these proficient AI weather models are actually publicly available, so you can go look at it. I'll share the slides, which will have some resources for you to go look at. And then a lot of observations are coming online, so this makes AI weather models prime to take advantage. And generative models like diffusions are actually really, really promising for probabilistic forecasts, useful for extreme weather outliers. Some have shown that NVIDIA has done some fantastic work in that space. How do you, but there are a lot of challenges in this particular space. So for example, if you train a model that is, if you train a model that is using data that is heavily skewed towards the developed world, it will lead to poorer performance in the global south, which is evident. And then more thorough benchmarks are needed. In absence of benchmarks, all models are optimizing for different tasks, which is not quite useful. We need standardization, like the physics-based models go through a lot of rigor for that. AI-based models carry biases from the NWPs, which they are initialized with, so that also needs to be fixed. And then domain experts, to Kai's point as well, domain experts are needed to be incorporated into model design. At this point, AI models are being developed in a silo. And then we all obviously need a robust train test deployment and monitoring these models, so to speak, to keep up with the rapid evolution. This is quite important for any ML development, especially something that of this importance. So finally, if you're interested, what does an operational AI weather forecast looks like? You can go look at this particular website. On the left-hand side, looking at hail forecast, severe convective storms. On the right-hand side, you're looking at the hurricane that is currently out there in the Caribbean. So please feel free to play with it. I think I leave this slide up, and I think this is the end. Yeah, I think I went over time. Happy to take any questions.
Thank you so much, Peetak. This was super insightful and in-depth of a lecture. So thank you so much for this. I'm sure there's many questions also for after. We do not have that much time left, so I'll focus on a few questions that were upvoted. And you have addressed a few challenges in this field already. And I think there's a lot of questions that touches upon those challenges from an open source aspect, from an ethical aspect, and biases. So I'd like to start with a question on ethical concerns / data ownership
Yep.
And it goes, are there any ethical concerns in the same way as LLMs and image gen AI, so image generators, where the models and cutting edge technology is held by big tech, and there are issues / problems with data ownership? So it touches upon many things, but yeah, please go ahead.
Well, that's an excellent question. I think we are lucky in that sense, because if you are keeping up with the news that is coming out from this particular domain, there's a great thing that is happening here, which is like whether enterprise as such has been in the public domain for the last few decades, ECMWF, NOAA, because it's such an important thing for life and livelihood. So basically the data in that particular sense is owned by the government, so to speak, owned by the public taxpayer. So it's available for free. It's available for anybody to use and play with. So that's great. There's obviously issues around data access. That's a different story. But in terms of model as well, like while big tech is at the forefront of this revolution until the last few months, currently, even government sources like ECMWF have released their own AI weather forecasting models, which is free to use, very permissive licenses. So basically, the goal is for you to then, so it does not necessarily have the same equity issues that you have from other domains, like in the world of LLMs, where OpenAI, I mean, should not take names here, but companies have proprietary data and proprietary models and so on. But that's not the issue in this particular case, because a lot of these code bases are made publicly available. Google has done that, NVIDIA has done that. And to that effect, ECMWF has released these models, released the weights, so anybody could actually operationalize these models if they really wanted. So I think in that particular sense, the data is, most of the data is publicly available. Some really good state-of-the-art models are publicly available. So yeah, I think so. There are issues, but not as much as in the world of LLMs.
I guess that's good to hear, right? And
yeah,
it would be great if we could share some of those examples, some of those data sources on the platform as well. I'm sure people are very curious about what data sources are out there and what models are out there that are openly accessible. It connects well to another question that we got in on biases of data. You mentioned that briefly throughout your presentation, that there is data and models can be skewed towards the global north often because of data availability and accessibility versus global majority countries / global south countries. And so there is a question that asks, would satellite data, so specifically satellite imagery, have inequality based on geography?
Yeah, no, that's a great question. So if you look at the, just the US and how much focus is there on satellites, like getting data in the US, like you have GO satellites, which are geostationary satellites collecting data from, the east and the west side of the US map, so to speak, geographical extent of the US, so to speak. But that's not the case for other countries. Global South, for example, does not have that. Like South America barely has a lot of like these satellites out there that are geostationary and so on. So I think I think that is an issue that needs to be solved. It's something that I think governments are working towards, private enterprises are working towards, but I think there's a lot needs to be done in that particular space to make the data equitable. And once that happens, you can incorporate those into your simulations, and that will help inform these models more accurately in terms of like correcting their forecast for these particular regions. Right now, they do a good job, but there's a lot to improve compared to the Western world, so to speak. So yeah, I mean, it's something that governments are actually investing in many countries, but it's just an expensive endeavor.
Absolutely, and thanks for addressing that. I think that's a very important topic, and underlying what you said, definitely lots to be done. I'd be curious, as a short follow-up question, if you would have any concrete recommendations or ideas on how this could be solved, at least on one level.
Yeah, no, I think the thing is, in trying to build a business as well ourselves, we are learning that people just don't do things out of the goodness of their heart. It has to make business sense. So I feel like if the local stakeholders, if they come on board and kind of like, it's a tough problem to solve, to be honest. It's a tough problem to solve because the West has had a huge leg up compared to the rest of the world because they've invested in all these things for a while. So naturally they have better resources. But I think it will come up when it will happen, I think, organically when there is a business sense for these things. There are a lot of corporations out in South America that are looking to get better weather data. I think they are deploying their own weather balloons and so on and so forth. So I think it will be a mix of citizen science, but also developing all these like low cost sensors that are collecting these data in real time at a fraction of the cost that it takes to collect that data in the US, but also kind of having some of these local groups coming in and creating a business sense for these investments to happen. Unfortunately, the way it works is that the government has to invest most of it, just the nature of how it works in weather.
Absolutely. That's a beautiful answer and closing words yet again. Thank you so much, Peetak. Thank you everyone for participating. There is a feedback form that has just been shared, so please make sure to fill that in. And we'll make sure to follow up on the platform on questions that have not been asked. So thank you again for Climate Change AI, for the organization and hosting the summer school. And I'm wishing you a good rest of your day, evening, and wherever you are in the world. Take care.